Hi guys, we are here to present our CS225 final project, and our group name is Niua, Niua. My name is Zehui Zhang. You can call me Ray.
My name is Chen Yuan, and you can just call me Chen.
My name is Rick Xin Kang. You can call me Caesar if you want.
So we want to use Dijkstra algorithm to find the shortest path to any airport from a given airport using routes.dat from OpenFlights. We use the weight for each edge, that is a function of number of stops and throughout the route to approximate its cost. In the next part, we will perform a strongly connected components analysis to find the number of SCC in the network. If we find the SCC is too few, for example, only one SCC exists, we will perform a random deletion of directed edges from the original graph. Or we may choose to delete the fly route that consumes very large time and run the SCC algorithm again. So the overall idea of the Dijkstra algorithm, we're gonna implement Dijkstra algorithms by using a BFS framework and a priority queue. We divide the overall algorithms into three steps. Step one, mapping nodes from input to integer index. Step two, construct an agency list, a adjacency list given the airport name to index map. Step three, run Dijkstra algorithm on the adjacency list.
So let me introduce our developing of the Dijkstra algorithms. So first, like the code we wrote on the right side of our slide, we mapping the airport name to index. For example, row 2 and row 4 stores the source and destinations of the airport name. And we also map each new airport name to a new integer index. And please go to the next slide. We then constructing our adjacency list, and you can see from our right side of our code, for each airport adjacent to another airport, we found the index of these two neighboring airports from the map. So that for each node's neighbors, we not only put the neighboring node index, but also its edge weight between the two nodes. For instance, we can see that the agency A dot push back 1B and the agency B dot push back 1A. So it's representing that B is connected with A by edge with less 1. And the next slide, please. Continue. So our Dijkstra logic is here. We initially start from node 0 with 0, 0 representing node 0 has a distance of 0 from 0. Then we find a pair of distance and node with smallest distance and pop it off the stack to loop over its neighbors. After that, for each of the nodes neighbor, we push it to stack with a new distance pair that can include a new distance to its neighbors and nodes index of its neighbors. Next slide, please. So our conclusion and our result of the Dijkstra algorithm is that there are 3,425 nodes in our undirected graph. The Dijkstra algorithms detect 28 nodes that cannot be reached from node 0. On average, the shortest distance from each node to node 0 is around 3.5. So therefore, we can conclude that it takes on average 3.5 flights to get to any airport in the network from the node 0 if using the shortest path.
Okay, I think we have done the Dijkstra algorithm, and for the next one, we're gonna have the Targent's algorithm. For the overall idea, we implement Targent's algorithm using DFS. The high-level philosophy is just that we keep track of a series of index from node, starting from node 0. We also keep track of the smallest index we can reach to any stack node in the current process using the low link. If we eventually can visit to the start node while it is still on track, like the low link current is equal to low link start, we find a strongly connected component.
So for the Taigen's algorithm implementation details, essentially we need to write a DFS helper to find a current strongly connected component using the low link and the index mentioned in the overall ideas. So the code down here is what I write for the DFS actually. Next slide, please. So in the Taigen function, we essentially loop through all nodes in the graph and call DFS on it if it hasn't been reached by previous DFS and hasn't been added to previous SCC. The code was on the right side. Next slide. So for the conclusion of the Taigen algorithm, eventually we find that there exist 8 strongly connected components. Some of them are very small connected components. Whether the other one is huge, representing above 99% of the airports, this means our common sense and reasoning, most of the airports should be connected in the components. So a flight can eventually fly back to its original airport after complicated roads.
Okay, so that is our final presentation, and I hope our group can get a very good grade, and I want to get an A. Yeah.
Thank you.
See ya, guys.